Hi there. In this video, we're going to talk about finite subgroups of SO3 and the Platonic solids. So we'll introduce the Platonic solids, we'll introduce the group SO3, the monohedral groups, the dihedral groups, the Platonic groups, and then we'll state one of the milestone theorems in this course, the classification of finite subgroups of SO3. Let's get started. So the Platonic solids are one of the centerpieces of mathematics. They're some of the most beautiful objects in all of mathematics, and we're lucky to get to study them in this course. Here's what they look like. We've got the solid, the tetrahedron. Right? It's got four faces, all triangles. We've got the cube. Six faces, all squares. Then we've got the octahedron. 8 faces, all triangles. So in one of your model building exercises, you're going to build physical models of these three Platonic solids, and I want you to pay special attention to the cube and octahedron because they are in some sense dual to each other. If we look at the vertices of the octahedron, we can see the faces of the cube. Right? So they've got a very strong relationship to each other. The last two Platonic solids are the dodecahedron and the icosahedron. So that's the whole family, all 5 of them, and they play a central and very important role in mathematics. Let's see. We're going to talk about the group SO3. The special orthogonal group is a special collection of matrices that preserve the relationship of orthogonality. We write it SO3 to keep track of the fact that we're looking at transformations of 3-dimensional space. And this is the rotational symmetry group of the sphere. So we have a sphere and we can rotate it and stay inside of SO3. So we write our sphere as S2 because the surface of the sphere is 2-dimensional. And we can say the definition of SO3 equivalently as being the orientation preserving isometries of SO2, right? So all of the rotations preserve the orientation of the sphere. So we write S with a plus symbol there to say that this is the orientation preserving symmetries. An equivalent way of stating the definition of the special orthogonal group is that something is in the special orthogonal group if it preserves the metric. Okay, so if for any pair of vectors v and w, the inner product of those vectors is the same before and after applying the transformation. The way that this connects up with orthogonality is that if we have a pair of orthogonal vectors, x and y, then when we apply our transformation t, they stay orthogonal. Okay, so the special orthogonal group is the collection of matrices that preserve the relationship of being orthogonal. Now let's get into the dihedral and monohedral groups. The monohedral group is the symmetry group of a one-sided regular n-gon. So it's an n-gon that lives in the plane. We can rotate it around, but we can't turn it over. So an example of something with monohedral symmetry would be a shape like this, where we add on some structure that prevents it from having a reflection symmetry. Here, all the symmetries we have are rotational symmetries. And this is a monohedral tiling because it doesn't have any reflective symmetries that allow us to turn it over. We use the notation Zn, and we've got the following presentation for that group. So this is another way of calling a monohedral group is the cyclic group with n elements. It's generated by a rotation about angle 2 pi by n about the center of the n-gon. So this group, Z3, can be presented as G, with G cubed being the identity, and that rotation G is by 120 degrees. Okay, so that's an example of a monohedral group. Just want to point out the size of this group. The size of the monohedral group is n, so that subscript n corresponds to the size of the group. Now let's have a look at the dihedral groups. The dihedral group is the symmetry group of a two-sided regular n-gon. Okay, so this is an n-gon where we allow reflection symmetries that allow us to turn over the object. So an example of a shape with a dihedral symmetry group would be an equilateral triangle where we're allowed to reflect and effectively turn the shape over. Right, so this would have symmetry of dihedral type, and we can generate this by using two reflections. So if we take a reflection R and a reflection S, then we're going to have that R squared is the identity, S squared is the identity, and those are going to generate a rotation about the center of the triangle in two lines R and S, which intersect at an angle of pi by n. Right, so this is going to have dihedral symmetry. So we're going to have R and S, where R squared is S squared is RS cubed, and we want that to equal out to the identity because it's a rotation of order 3. And the angle here will be pi by 3. Okay. Notice with the dihedral group that we have that we have two n elements. So we have an n here and a 2n here. So the index of the dihedral group is the number of sides of the n-gon, and an n-gon has two n symmetries. So just something to be careful of, the notation there. Okay. Now let's talk about the Platonic groups. The Platonic groups are very special. We're going to call delta the tetrahedron. So that's this guy. And we're going to write the symmetry group of the tetrahedron as being isomorphic to A4. So that's the alternating group on 4 elements. And we're going to get into exactly how that group arises in class. We have that A4 has 12 elements. And I just want to point out one way of thinking about those 12 elements. So the tetrahedron has 4 faces. And each of those 4 faces has an order 3 rotation associated with it. So that gives us 3 rotations per face, and we get a total of 12. Okay, so that's a heuristic on how to remember the size of this group. Now, let's move on to I3, the cube. The idea for this notation is that we're saying I cubed is like an interval cubed, right? So we take a particular interval, we put it in the x-axis, y-axis, and z-axis, and we get I3, the cube. Okay, the rotational symmetries of the cube are isomorphic to the group S4, so all the permutations of 4 objects, and we have that S4 has size 24. So one way to think of this is that the cube has a total of 6 faces, and each of those 6 faces comes with 4 rotations associated with it. Okay, so again, this is a heuristic on how to remember that. Also, by duality, the symmetry group of these two objects are the same. So the cube and the octahedron are going to have the same symmetry groups by duality. So the symmetry group of the octahedron also has 24 elements. Okay, now we're going to let dode denote the dodecahedron, and the orientation preserving symmetries of the dodecahedron are isomorphic to A5, the alternating group on 5 symbols, a very, very important group in the history of mathematics for reasons that we'll get into in class. It has size 60. The dodecahedron has 12 pentagonal faces, so 12 times 5 gives us 60 elements. And again, by duality, this is going to be the symmetry group of the icosahedron. Excellent. So now we've got all the groups that we need to state the major classification theorem. So suppose that we've got a finite, non-trivial subgroup of SO3. Right? So by finite, we mean it has finitely many elements, and by non-trivial, we mean that it's not just the identity element. So the structure theorem tells us the following, that G has to be isomorphic to one of the following groups. It's either a monohedral group for n greater than or equal to 2, a dihedral group for n greater than or equal to 2, the symmetry group of the tetrahedron, the symmetry group of the cube or the octahedron, and the symmetry group of the dodecahedron or icosahedron. Right? So we've got these two infinite families, the monohedral and the dihedral groups, and then we've got these three special groups corresponding to the tetrahedron, the cube, and the dodecahedron. So we're going to get into the details of how to prove these things in class. Thank you for watching.